This is the first problem that I'm doing for chapter 21, and the problem reads: the electrons in the beam of a television tube have a kinetic energy of 2.40 times 10 to the negative 15 joules. Initially, the electrons move horizontally from west to east. The vertical component of the Earth's magnetic field points down toward the surface of the Earth and has a magnitude of 2.00 times 10 to the negative 5 Tesla. In what direction are the electrons deflected by this field component, and what is the acceleration of an electron? So here are the images that I'm using, and I have to admit it really wasn't easy to find the right images. For example, for the right hand rule from our book, I took this image and this image here, and we'll see what we can do with them because they're absolutely correct here. I just wish that the hand would be turned in a just different way. We'll see what we can do here. I grabbed this image here from the book. So that's a television tube, and I realize these days we pretty much have the LCD screens for our televisions. These are, what you see here are the television tubes, also called Brown's tubes, after the person who invented them more than 100 years ago, around 1900. But this is what we used until very recently, and so you find these still in physics books. And as far as an example for the deflection of an electron beam in a magnetic field, they're just a very good example. And you might still see them. Oscilloscopes still use these as well if you have an older television. Okay, any case, so I took this image here, then I took this image, and notice what I did with it. I mirrored it, so you see the N and the S spelled backwards and everything else backwards, because I wanted to have the magnetic field go down just like the problem said, and the charged particle, the electron, I will change this here very soon to a negative. The charged particle coming from the left because the problem says west to east. And if I had my cardinal directions actually on a map, north up and so south down, then of course I have west on my left and east on my right. Okay, let's start over here with this television screen where we have actually the magnetic field pointing up here, and I just want to apply the right hand rule. So I turn this one here, and now my magnetic field is pointing up in my right hand rule, just like it is here. And the velocity, I know it points towards the upper left. Well, here it points to the upper left, while here it points to the lower left. But let's just make it coming out of the picture, okay? And then the two are the same, so both of them are coming out of the picture. In any case, the force is to the left, but this one is a positive particle. The right hand rule works for positive particles. So for positive particle coming out of the screen, that means out of the paper, the deflection will be this way over here to its right. Now here we have an electron, a negative particle coming out, so the force will be in the opposite direction. So imagine that here the force is pointing towards its left, coming out of the picture, and that's what we can see here. It's coming towards its left. Alright, so we have figured that out. So that one is actually correct. We have to rethink a little bit every time we use a negative particle. And again, we also have to rethink here because the pictures that I found of right hands are just not totally perfect for what I want to do here. You know, I wish that the hand would be a little bit turned, but they're not, and I'm bad at drawing, so I just have to live with this. Okay, now over here I'm going to turn around like this, and that's actually not too bad if you look at it. There we go. Okay, so here the magnetic field is pointing down just like here. The velocity is left to right just like here, and now the force for a positive particle is this way here. Okay, that means a positive particle should go this way, but remember I flipped the image, I mirrored it. Okay, so the positive particle should go this way. Now I do have a negative particle, so I'm going to change that to a negative. First I'm going to make a little circle here, hopefully. There we go, maybe not. Try it again. click on properties for this little circle and solid fill. Sure, orange maybe. There we go. That's good enough. And then I'm gonna put a negative in here. So this is a negative particle. At least I tried to put a negative in there. There it is, negative particle. So now we look at it and we say, okay, magnetic field is down, velocity is this way, the force on a positive particle is this way, but since we have a negative particle, the force on the particle is this way, and now the mirrored image actually describes correctly the negative particle, which makes sense because I mirrored it. Therefore, I have the force in the right direction now for a negative particle. Okay, having that figured out, the answer is that it is deflected trying to write here, deflected towards its right. And if we look at the electron in a television tube, that makes sense here as well. In this case, the electron is deflected to the left, but that's because the magnetic field is pointing up. So here, magnetic field pointing down, electron deflected to its right. Here, magnetic field pointing up, so electron is deflected to its left. So it does make sense. We figured that out. And again, it's not the easiest thing. If you get the hang of it, that's great. Otherwise, practice. All right, the second part is actually what's the acceleration? Well, what they give us in the problem is they give us a kinetic energy of 2.40 times 10 to the negative, let's see, how much is that? 15 joules. Okay. And kinetic energy equals 1/2 mv squared. So first I have to solve for the velocity, because that's what I then need for the equation that will then give me the force exerted by the magnetic field on the charge. So I'm going to have V equals 2 times the kinetic energy divided by the mass, and that would in this case be the mass of the electron. Take the square root, and when you plug that into the calculator, these are all standard units, so it will come out to meters per second. And let's see, when I do that, square root of 2 times 2.40 10 to the negative 15 divided by the mass of the electron, and that one is 9.1 times 10 to the negative 31, and I come up with quite a tremendous speed of 7.2. It's hard to squeeze it in here. 7.2 times 10 to the 8th, no, 10 to the 7th meter per second. So this is quite fast here. That's approximately, let's see, 72 down, approximately in the neighborhood of like 45,000 miles an hour a second. 45,000 miles a second, that's how fast the electron is. All right. Now I got the speed, and now I use the equation for the force that the magnetic field exerts, and that one is F, force equals magnetic field times the charge of the particle, which in this case is an electron, times the velocity that I have just computed times the sine of the angle, and the sine of the angle, I'm sorry, the angle would be the one between the velocity and the magnetic field, which is 90 degrees. So that would mean that I take the sine of 90 degrees, which is simply 1. And then that one here will be, again, standard units. So this here will be in newtons. So I plug in numbers. There is a given magnetic field of 2.00 10 to the negative 5 Tesla times the charge of the electron is 1.602 10 to the negative 19 coulombs times velocity that I just calculated of, what was it again, 72 million something, and I come up with a force of 2.3 times 10 to the negative 16 newtons. Now, a moment ago, that velocity seemed extraordinarily large, and yes, the electrons are that fast. In this case, the force seems extraordinarily small, but that's because the electron is so tiny, so it's just going to be a little force on a small mass. And then really the last thing that I have to do here is acceleration equals force divided by the mass of the electron, and at this point here I'd be dividing by 9.1 times 10 to the negative 31 kilograms, and I'm come up with this huge acceleration in the neighborhood of like 10 to the 14 meters per second squared, and so the electron is quite a bit deflected, but with that acceleration, but it doesn't take long to get to the front of the television screen. So the total deflection, the distance over that tiny amount of time that I didn't calculate, that distance is going to be in the neighborhood of only a few centimeters, inches. Okay, in any case, oops, didn't make me to do that little thingy here. Oh great, now I can't get rid of it. There. So you will come up here with meters per second squared. All right. The next problem reads, a charged particle enters a uniform magnetic field and follows the circular path shown in the drawing. Is the particle positively or negatively charged? Why? The particle speed is 140 meters per second. The magnitude of the magnetic field is 0.48 Tesla, and the radius of the path is 960 meters. Whoa, that's a huge semicircle. That's more than half a mile. Determine the mass of the particle given that its charge has a magnitude of 8.2 times 10 to the negative 4 coulombs. Okay, so here's the magnetic field pointing out of the paper, out of the screen. The particle is going this way up and deflected to its left. This time around, fortunately, the image that I got for a hand is fitting the picture virtually perfectly. I'm so glad. Of course, there's one little thing in there, you'll see in a moment. So if this is a positive particle and it moves up, which it does, and the magnetic field is pointing out of the paper, out of the screen, so pointing towards us, which it does, then the force is to the right, which it is not. Consequently, this is a negative particle. So that was easy to figure out. This one is a negative particle because the force points in the other direction. So a negative particle, whoops. And I actually should have typed that, then I wouldn't have this strange handwriting. So negative particle, I think I'm going to type here. Because of right hand rule 1, the force points to its left with magnetic field out of the paper or screen, and the force, yeah, points to its left. Okay, make this maybe a little smaller. There we go. All right. So part B is try to figure out what the, let's see, the masses of the particle, right? Determine the mass of the particle. So again, that takes the law that gives us the force of the particle. By the way, this one is actually called the Lorentz force, and this one here is the magnetic field times the velocity, times the charge of the particle times the velocity. In this case, they don't say what kind of particle it is, so I just write little q for the particle, times the sine of the angle. And we can see that the angle between the initial motion and the magnetic field, so the initial motion is going up and the magnetic field is coming out of the paper, and so that's a 90-degree angle. So the sine of theta actually comes out to exactly 1. Sine of 90 degrees is 1. Okay, and then this one is given in the problem. That's the, let's see how much it was. The magnetic field 0.48 Tesla. Then the Q, let's see, actually the Q is, the charge is given 8.2 times 10 to the negative 4 coulombs. And then the particle speed is given as 140 meters per second. And then we could calculate the force. Now what they do in the book is they say, okay, so we determine the force. How do we get the, in this case, the mass out of it? Well, it's mass times acceleration. And then what happens is this is in a circle, so the force law for centripetal acceleration applies, and that one is, we go a few chapters back, mv squared over r. And remember that r was also given in the problem. So that equals magnetic field times charge times velocity. And if we solve for mass here, and I do the algebra already in the book, I just repeated it here, then it's going to be, let's see, fraction bar magnetic field times charge times the given radius divided by velocity. One of the velocities cancels, but then it appears in the denominator, and then it's just a matter of plugging in numbers to come up with a mass for this particle in kilograms, because we are using standard units, so it has to come out with kilograms.